Welcome to the podcast. This is Mr. White.
And Mr. Sadler.
We're going to do a little AP Plus, Chapter 2, Section 9. And we're going to talk about energy versus work in terms of scalar and vector. So the work equation, you remember, is force times the displacement, or force times distance. And force is a vector.
Right.
So work has to be a vector.
Right.
Direction counts.
Because I can push something to the right or to the left, or stop something moving to the right by pushing to the left.
And we can have forces that do negative work, that steal the energy from a system, like friction.
Friction,
Yeah.
right.
Energy, however, is a scalar. And we know this because when we look at things like gravitational potential energy, kinetic energy, and elastic potential, and specifically we look at their equations, all right, we see things that would indicate that direction doesn't matter, like mass. If an object's moving, it has kinetic energy. It doesn't have to be that an object is moving in a positive direction. The spring constant is more of an engineering idea than it is anything. It's just a property that the spring has. That's the K value. It's how much do you stretch or compress it. It doesn't matter which way you do it. It's still going to have energy. The height of the object, etc. So with respect to the ground, you can make adjustments any way you like there. Scalar, vector. They ask you to do some problems in the AP Plus. Let's look at number 1. It says a roller coaster is poised at the top of a hill that is 50 meters high. H is 50 meters. How fast will it be going when it goes over the top of the next hill on the track that is only 30 meters high? So H1, H2. 30 meters. Okay. From a practical point of view, why is it advantageous that this ride is mass independent? So mass doesn't matter. Question mark.
Oh, why doesn't mass matter in this case?
Right.
Because it's the same
let's
roller coaster
let's
going
work it
over
out.
both. Yeah.
First scenario, I'm at the top of the first hill. I go down. I go up to the top of the second hill, right?
Right.
So here's my roller coaster cars, exciting stuff. All right. Here, what kind is it moving at the top of the hill at that brief moment in time?
Well, no, right? Because
No.
it's right.
And so it has what kind of energy?
Gravitational potential. It's not moving. It might be moving right or left, but it's not moving up or down.
Correct.
Right.
And at this guy over here, it's definitely still got some height, but
Right.
it's also
Not moving up or down.
it's got to be moving, doesn't it?
Well, it's got kinetic energy too.
So
right?
let's go back to this just briefly. Right before we leave, each car at the top has no motion.
Right.
Do you ever stop at the top of the second hill?
No.
No, so there's some kinetic energy
Right.
there. So what we would say is that energy initial and energy final have to be the same because of energy conservation.
But we've picked up speed because we are losing gravitational potential energy.
Right. So this is just gravitational potential, but this is gravitational potential plus
Kinetic, right?
And so I start working on some equations. And I realize something. When I look at every term, I notice that every term has a
M.
m. And so in reality, the mass of the object doesn't matter at
Right.
all. And so I could figure out how fast pretty easily because I just got to subtract GH2 over. Okay, and I'm going to get this. And I do a little bit more math. And I can figure out how fast it's going. So 2 times 9.81 times the difference of 50 minus 30, take the root. So let's see, square root of 400, roughly about 20 meters per second. And what you notice is that the mass, that scalar thing, doesn't matter.
Right.
It also doesn't matter what direction my roller coaster is going. It still has gravitational energy because it's above the ground. Same story here, and now it's moving, so it still has kinetic energy. If the car was going backwards, would that change anything with our problem? It would change nothing at all. All right? So energy is a scalar, work is a vector. Signing off, this is Mr. White.
And Mr. Sadler.